Hi, my name is Ellie Hummel, and for the past few months, my partner Jane and I have been working on our project, exploring the effectiveness of various nanomaterials on the removal of the pharmaceutical drug estradiol from tap water. So 41 million Americans are exposed to drug-contaminated water every day. This problem is a result of decades of pharmaceutical drugs being dumped into toilets and flushed into the sewage system, additional active ingredients being carried in from urine, and most importantly, additional runoff from the healthcare industry. As a result, of the sewage system not being able to equip this high level of pharmaceutical contamination, it is leached into surrounding groundwater, streams, bays, and estuaries, and any other naturally occurring body of water. In fact, in a study done by the American Geological Study, 80% of streams and rivers they sampled have been found to have pharmaceutical drug remains in them. And this number is only compounding as poor waste disposal continually occurs. So in addition to being present at rising numbers, pharmaceutical drugs also have a very harmful effect to both animals and plant life. For instance, ibuprofen has been demonstrated to interfere with the cardioprotective properties of aspirin. Some of the new generations of cyclogenase 2 inhibitors might interfere with bone healing and regrowth after fractures. Furthermore, caffeine may enhance the effects of certain analgesics. In another study done by the Citizens Campaign for the Environment, it was found that pharmaceutical drug remains in tap water actually affect things such as antibiotic resistance, hormonal imbalances, and other things. So although these pharmaceuticals aren't present in our tap water in high amounts, it is very possible that after years of continual exposure, they may have unseen and unpredicted impacts on our health. Current methods to remove pharmaceuticals from tap water do exist, however they're limited by two major aspects. First, conventional methods remove pharmaceuticals at a rate below acceptable ranges, leaving a potentially harmful amount of trace remains behind. Second, the methods lack the cost effectiveness needed for worldwide application due to the time necessary to remove pharmaceuticals and the one-time use nature of these methods. The most current methods of pharmaceutical removal include reverse osmosis. However, reverse osmosis is not sufficient enough to remove these pharmaceuticals. And in a study done by the Chittobaram Pharmaceutical of the Civil and Environmental Engineering at the Israel Institute of Technology revealed that reverse osmosis could only remove 45% of pharmaceutical and personal care products in aqueous solutions. Furthermore, multiple studies on the removal of pharmaceuticals from water conclude that the time it took to absorb pharmaceutical drugs using the current method was below the effectiveness line for it to be cost effective. So it's clear that new technologies are needed to remove pharmaceuticals from tap water. As a result, my partner and I decided to look at nanotechnologies. Various aspects of nanomaterials are useful to the removal of pharmaceuticals from tap water. In fact, according to a study done at King Saud University, carbon nanotubes, nanoscale metal oxides, and nanofibers are most effective at absorbing organic compounds from water due to their high specific surface area, the selective in the number of absorption sites, tunable surface chemistry, and reusability. Furthermore, in a project to analyze metal nanoparticles, carbon nanotubes, and nanofilters for removing pharmaceutical drugs from wastewater in hospitals, a combination of these nanoparticles were able to remove pharmaceutical drugs at a rate of 80%, indicating a possible application of nanomaterials in water purification. So, we wanted to focus on both graphene and carbon nanotubes in our project, and specifically look at one drug, estradiol, because it's of particular interest. Estradiol is a popular form of estrogen, a female sex hormone produced by the ovaries. It is used to treat symptoms of menopause, such as hot flashes and vaginal dryness, burning, and irritation. Due to its common structure and popularity, a filter that is developed for it could be widely used and easily applied to other drug types. So therefore, the first purpose of our project is to determine which nanomaterial has a higher absorbency, because this would allow us to see which one would actually affect water and the water purification system better.
So once we did the first part of the project where we determined whether the absorbance was high enough between the pharmaceutical and the nanomaterial for the nanomaterial to remove the pharmaceutical from water, we then had a second purpose, which was to perform a comparative analysis between the graphene and the carbon nanotube to see whether the absorbance measures were significantly different, to say that one nanomaterial is more effective at removing the pharmaceutical from water than the other nanomaterial.
So our first hypothesis is that graphene would have a higher absorbency energy than carbon nanotubes due to the fact that it is a 2D model, making it more spatially economic, and therefore allowing it to have a higher absorbency energy.
So the hypothesis for the second purpose was that graphene would have a significantly higher absorbance of the pharmaceutical compared to the carbon nanotube. And we thought this because although they have the same basic structure with a hexagonal tiling made out of carbon atoms, graphene is a rolled out sheet rather than a rolled up sheet like carbon nanotubes are, so there is a much higher surface area on graphene compared to carbon nanotubes. A quantitative quasi-experimental method using computational simulation, and we used a computational simulation model called VASP. And VASP uses quantum mechanical equations to calculate the ground state of a group of atoms. And we need to calculate the ground state because the ground state is the lowest energy state of the molecules, and it's in this state that we could calculate the total energy of the system. And so once we used VASP, we had a series of 3 main steps to complete this project. And the first step was to create the binary structures of the nanomaterials and the estradiol, so we could then relax them on VASP, and then once we got the relaxed structures, we could then create systems with the nanomaterial and the pharmaceutical to input into VASP and relax those. Then once we relaxed those, we got the energies of those systems. Then using the energies that we got from the 2 relaxations, we could then calculate the absorbency measures. And so in order to use VASP, we had to create a series of 4 main files, and the first of these files was called postcar. And postcar describes the position of all the atoms and the molecules, and so we used a program called Material Studio to do this. And Material Studio allowed us to visually make these molecules. Then once we visually made these molecules, we could then upload the coordinates of the atoms onto the postcar file and use this postcar file to run the simulation model on VASP. And so there are 3 other files that we had to create called K-points, NCAR, and POTCAR. And POTCAR were already they were provided by the VASP computational simulation model package, so we didn't have to modify them that much. And the only cases where we had to modify them was because of absorbency energies that were calculated that indicated chemical bonds, which would not have happened. So we knew that something was wrong and had to go back and change the K-points file, the NCAR file, or the POTCAR file to make sure that the absorbency energies indicated physical bonds, which is what we were looking for. And so once we relaxed the structures, the binary structures of the nanomaterials and the estradiol, we got back a output file called AUXICAR, and AUXICAR had the final energy of the system. And then it also had a postcar file containing all the relaxed coordinates of the molecules, and then with these relaxed coordinates we could then create systems. And we once again did this on Material Studio, and we created systems by combining the coordinates of the relaxed estradiol and the relaxed nanomaterial. And then when we did this, we made sure to have the estradiol angle the nanomaterial at 3 different angles to try to mimic all the possible different interactions that could happen between the nanomaterial and the pharmaceutical. So as seen here, we had an angled one, a vertical angle, and a parallel angle. So then once we relaxed these structures onto VASP, we were then able to get back an output file that contained the final energy of the whole system. So then we now had the energies of the systems and the energy of the individual molecules. So then we were able to calculate the absorbency by taking the energy of the system and subtracting the energy of the nanomaterial and the energy of the pharmaceutical. And so here you see the data, and we repeated this process twice. Once without a layer of water between the nanomaterial and the pharmaceutical, and another time with a layer of water between the nanomaterial in the pharmaceutical.
So our first set of results, which was looking at the absorption energy without a water layer, found that there is no significant difference between the absorbance energies of carbon nanotubes and graphene at any of the bond angles they were positioned at. So this includes both parallel, perpendicular, angled, and angled. And then we took the average of all three bond systems, and there was still no significant difference. So this shows, that in fact, without the water layer, they both have similar absorbency energies, and either could theoretically be applied with water to make an impact.
The bar graph of the absorbency energy after we added a layer of water in between the nanomaterial and the pharmaceutical. And as you can see, compared to the other graph, after we add a layer of water, the absorbance energy of the graphene had stayed relatively the same with about 4.5. However, after adding a layer of water in between, the carbon nanotube absorbance energy had decreased by about 0.4, so that the absorbance energy of the graphene was now higher by about 0.3. And after collecting this data, we performed a Welch t-test, and we had a t-value of around 21, which was greater than the critical value of 3.1, meaning that there was a significant difference in between the absorbency energy of the carbon nanotubes of the graphene, to see that graphene was much more effective. And you can also see this significance by looking at the error bars, and as you can see, they don't overlap, which means that there's a significant difference.
So in conclusion, our first hypothesis is not supported by our data because we predicted that the graphene, because of its higher spatial economics, because it is a 2D molecule, would actually be more absorbent. While in fact this is not true, both carbon nanotubes and graphene have a not significant difference in absorbency energies. And although graphene was consistently a little bit higher, this difference was not significant. So in fact, either molecule could be used and have relatively the same absorbency energy. In the future, Jane and I would like to apply the results we have learned here about the effectiveness of graphene versus carbon nanotubes and look specifically at developing a filter which can be economical and universally applied, while also being more effective than the current removal rate of 45%. Thank you so much, and we hope you have learned a lot from our presentation.